In this section, we're going to talk specifically about the rate law. Now, by definition, when we talk about the rate law, we're talking about the relationship between the reaction rate and the concentration of the reactants. So the rate law is specifically only about the amount of reactant being consumed. So you can think of it as a very basic equation of reactant to products. This is really all we're talking about when we deal with the rate law. Now, one of the things I want to point out is that you cannot tell what a reaction rate is simply by looking at an equation. So when you look at these two equations, we have the breakdown of ammonium, we have the breakdown of nitrogen dioxide. We see very different rates associated. So when I look at the ammonia, you see this very definitive downward path. When we look at the nitrogen dioxide, we get a very different reaction. So again, you cannot predict the rate by the equation. You can't simply look at a chemical equation and know the rate. The only way you can determine it is experimentally. So we have our basic equation. This is basically what's known as the rate law or the rate equation, this part right here. Now, the next point to pick up on is the order of the reaction, and that's this little exponent here. The exponent tells us the order of the reaction. The reason we care about the order of the reaction is it gives us a little bit of insight into the mechanism. And the last thing, which we're going to spend a little time with on the next slide, is the K here. It's what's known as the proportionality constant or the rate law constant. What's unique about it is that it varies, and it varies by the reaction, it's impacted by temperature, it varies by whether you're talking about the integrated rate law and whether it's an integrated rate law for the particular order of reaction, etc. The other thing to keep in mind, it can be measured, it's measurable. Okay, so let's talk about some examples. First and foremost, when we look at concentration and rate, as I mentioned earlier, you can only determine these experimentally. So you have to do a series of experiments where you modify the ratio, the concentration of the reactants. And so you vary the concentration of reactant and you get a subsequent rate, a subsequent speed for the reaction. So what we look at when we look at something like this, if you look at where it says compare 1 and 2, and you look at the concentration of the NH4 here, it was doubled and the rate doubled. When we look at the NO2 on the other hand then, and we compare 5 and 6, so here's your experiment 5 and 6, we doubled the concentration and the speed doubled. So what we see is we see a direct relationship between both the NH4 and the NO2. So the thing to recognize is I have, in essence, a proportionality. In other words, the rate was proportional to the change. And that means that these were first order reactions, both of them. So my new rate law basically is my rate law constant, my concentration of ammonium, my concentration of nitrite, and there's an assumed 1 here. So I have an assumed 1 here and assumed 1 here. What's cool about this is I have now a very simple calculation. So my overall reaction, I add my 1 here that's assumed there, plus the assumed 1 here, and I have an overall second order reaction. Now, the second thing that's very cool about this is if I go back to my rate law, right? I look at my rate law. If I go back to the reactions, I can choose any one of these equations and I can substitute that information into this equation and I can determine the value of K. So if we do that, we substitute one of the speeds, concentration of ammonium, concentration of nitrite, multiply them, divide, here's the value of my K. So you can always solve for K once you've identified the exponents that go along with your concentration. And that's in essence what the rate law allows you to do, is to identify the order of reaction for each reactant, the overall order for the reaction. In other words, we have to account for each reactant and we can calculate K. Now, as mentioned before, we have 3 basic orders of reactions. We have 0, first, and second. When we talk about a 0 order reaction, in essence, we have a rate that is constant regardless of the concentration. In other words, literally the rate is independent of the concentration of the reactant. Okay, so it's not dependent at all, it's independent of it. So we keep a constant rate. What's cool about this is two things. One, when we graph it, this graphing is actually based on an integrated rate law, meaning we've applied calculus to it. What's cool here is my rate is actually equal to k, because a to the 0, whatever my concentration is to the 0 is 1. And so my rate is my constant. And you can see what the units are. And the only reason I'm including the units is to remind you that K has variable units. It depends on the reaction, it depends on the reaction mechanism, all of that stuff. But again, zero order doesn't depend. So you can see I get this perfectly straight line of concentration versus time. As we saw in the example, first order reactions, we see a direct relationship. So if it doubles, my rate doubles. If I half the concentration, my rate is cut in half. So now I have this, in essence, rate law equation, and I see this curve. I don't really like curves, so we mathematically treat it, and that's what our integrated rate law allows us to do, and this is where natural log comes in. So when we treat our rate with a natural log, it produces a straight line. Notice we have a negative k slope, in essence, and the straight line gives us more of a direct cause and effect relationship. So if I take the natural log of my concentration, I get this nice straight line versus time. Now, second order processes look very similar to our first order processes. We have curved lines. The big difference is here I have an exponential relationship. So if I see, for example, if I double my concentration and I get a rate that is literally 4 times the original rate, that's a second order reaction. That means I have this exponential relationship. And the integrated rate law then allows me to treat that. Notice 1 over AT, and sure enough, as soon as I put 1 over my concentration, I get a straight line. So ultimately the point of the integrated rate laws is to allow us to find these direct relationships and the graph demonstrates that direct relationship so that we can figure out whether we have a 0 first or second order reaction. Now, ultimately, so I don't think you're going to need to know the integrated rate law. However, you do need to know the treatments. And by treatment, I mean the mathematical treatment. Do we have a straight line to begin with of concentration versus time? Or does the application of a natural log make a straight line? Or does 1 over, what's going on there? Let's get rid of that. Does 1 over the concentration create a straight line? So by mathematical treatment, what we're saying is if you graph your initial data, what does the initial data look like? Do I have, a perfectly straight line, or do I have some kind of a curved line? If I have a curved line, I know I'm dealing with a first or a second order reaction. So then it becomes, does natural log give me a straight line, or does 1 over the concentration give me a straight line? In which case, depending on the treatment, depending on what gives you that straight line, that's how you're going to identify the zero first or second order reactions. And that's in essence what our rate law is. And that's what the integrated rate law is. So the integrated rate law is this combination of the change in time, change in concentration, and the graphical analysis.